Okay. So let's start off with, let's see. Oh, we gotta connect to Zoom. I forgot to do that. Let's see if we can connect. That doesn't seem right. It's not Valentine, our student, it's the other student. Where is the other student from? It's from Imperial. Oh, hello. How are you?
Good, how you doing?
So I guess you're able to join in today.
Yeah, sorry about that. I've been doing football camps that went till like 5 o'clock every
No
Monday and
worries.
Wednesday, so sorry about that.
No worries. You've been able to get the videos?
Yep, I've been using those to help me out with homework and stuff.
Excellent. Let's see if I can. Let's see. Where are you coming? Where are you connecting from?
Overton, Nebraska, my classroom where I teach at.
Okay. Where is that near?
It's about an hour or so east. It's right by Lexington.
Okay. And then let's see. I need to check on one more student here. I'm pretty sure. Go away. Oh man, I'm gonna get hungry during class. I forgot to eat lunch. What is my password? Something like this. Okay, let's see. We're in physics. Where is this one? I guess it is an Imperial. Okay. So let's try to connect to Imperial really quick, see if that'll work. All out. So Imperial 72. See if she's there. If she's not, we'll just invite. All right. All right. So let's see here today. Like I said, we had some questions about stuff for the test. Let's take a look at our calendar. When is the test due? Tomorrow or Friday or something?
I think it's Friday.
Yeah, Friday, exam 1 through 5. And homework 5 due today. Homework 6 due Monday. We're still in a pretty good place here. We can make up some time later if we need to, I think, but we're in a pretty good place. So let's go ahead and start off with questions from chapters 1 through 5. If anybody has any last minute questions before they take the test. I did have the Does anybody have a particular question from a particular homework assignment or 27 on chapter 5? Let's take a look at that.
Yep. Thank you.
So in this problem we have this is a fun problem. This is, wait a second, is this chapter 5? Were we doing friction in chapter 5 already? Oh yeah, we were. Yeah, okay. So in problems where you have a rope or a string or a chain or something between two objects and it turns a corner like this, it can be a little bit tricky because we often don't remember kind of what is, or we don't realize what's connecting these two things. And we also don't realize that these masses are actually the same system. So when this whole thing accelerates, you have to consider both masses as accelerating. You can't just consider one or the other as accelerating.
Sounds good.
So for example, if this thing is,
Sounds good.
what is my strength of friction? So this is part A. So in part A, they're just asking what's the maximum strength of friction, right? So that one doesn't really require much work or thinking as far as all the parts go. So for part A, all they're asking for is the maximum coefficient of static friction. So you're going to use the equation for static friction, which let's go to our whiteboard here. And it looks like this. I haven't shared my thing with you yet here, so for any object that's on a flat surface and there's no forces up or down on it except gravity, then it's going to look like this. The force of static friction, let's actually use do like they did. I think in the book they actually like to use little f for friction and static. Now, some of you may have noticed that in the book they'll use one variable and in the homework they'll use another variable. That happens all the time in physics. It's just something you have to get used to. I apologize for it, but everybody since like Galileo has done that. It's just one of those things. But anyway, so that we're going to use this one. This is the static force of friction, and instead of having a greater or a equal sign there, they put a less than or equal to sign here, right? So this is less than or equal to the mu static times the normal force, and the normal force in this situation where you have just a block sitting on a table, the normal force upward is going to exactly cancel out the weight force downward. And the weight force downward equals m times g, where this is going to be a negative force here, m times 9.8, right? Whatever the mass is. This has some mass. And so the normal force is going to be that exact same number, but opposite. In other words, the normal is going to be positive m times g, right, in this situation. If you're on a slope, that's not the case. But, so that tells us what n is, so we're good there. The mu sub s is something that we can just pick up out of the problem. It's just given to us. But how do we use this equation to find the maximum? The maximum always happens when you change this to an equal sign. The equal sign is the maximum static friction you can get. So that's how you calculate that. That's part A. Pretty simple. Man, we should order some pizza. Oops. Which one was it again? 15? Or 5?
27.
Sorry?
27.
Oh. I obviously remembered it really well. Okay. So, let's see here. Let's say the two masses are moving, they're released, so you have our static friction coefficient. They've given us that, so we've done part A. Part B. What is the maximum mass for M2 that this frictional force could hold up. So this is where it starts to get a little bit more tricky. We have to start thinking about things. So what we need to do is we need to say, well, if this thing has a frictional force backwards of a certain amount, how much force could it hold up from here? Well, the force is transferred through the wire or through the string or whatever, right? So if we go back to this, if we go back to our problem here, clear this out, then we have a frictional force that is pulling this way. The static frictional force is pulling this way on this block. And on the other side of this block, you have the tension in the string pulling on it, right? That's what the force diagram for this block looks like. And then you have this pulley here. This tension goes over this pulley, and this same tension is going to be holding up this other block here. And what's pulling down on this block is the weight of this block. So this is mass 2. This is mass 1. Right? So down here we have our weight, which equals mass 2 times gravity. Right? And the only thing holding it up is the tension in this thing, and the tension in this thing is actually created by the friction over here. So this friction is pulling this way on this block, the tension is pulling this way on this block, and all the forces on this block have to add to 0 because it's not moving yet. So that means the friction has to equal the tension. The tension here has to equal the tension here, right? And if this block and this block aren't going to move, then the tension here and the weight here have to be equal as well. So in other words, the answer to the second part should be the same as the answer to the first part. Well, it shouldn't be the same because they're asking for the mass. So what you're going to do is you're going to plug in the weight. The friction is going to equal the weight, so you'll plug in your friction into the weight, and then you'll solve for the mass by dividing by 9.8 on both sides. And that will give you the maximum amount of mass you can hold up. Now, part C. Now they're telling us the value for mass 2 that's on the diagram is going to be our mass. So what it is, mine is 899 and 666 up there. We're going to find the magnitude of the net force on the system. So the net force is going to be the sum of all the forces. Well, according to our previous diagram, we essentially have two forces that are external to the system. We have the frictional force, if this is all in one system, and we have the weight force of this one, right? So those two forces are the only external forces on this system. Now they don't behave in a straight line, and that's one thing that really confuses people in this problem. But because there's a pulley in between them and a rope on that pulley, it's as if they're behaving in a straight line. So you can actually add them together and get the total net force on the system. But one of them has to be negative and one has to be positive, and you have to kind of decide. You're essentially going to take the difference of the forces. Just take them both as positive forces and take the difference, and that will give you the answer. But then whichever one is greater is going to tell you which direction this system is going to what the system is going to do, essentially. So if the static frictional force, if the maximum static frictional force is greater than this force, then what is this system going to do? If your maximum static force is bigger than any other force pushing on it, is it going to move? What does static frictional force do? Static means no moving, right? So if your static frictional force is greater than the other force, then there's no moving. And what's going to happen is that these forces are going to cancel out, because this force will essentially meet, it will counteract any force up to its maximum value. Once it gets to that maximum value, then it will start to move. right? So if this one is greater, then the net force is going to be this one minus the static frictional force, and then it will start to move. If this one is greater, then the net force is going to be 0 because it's just going to equal this one. That's what that less than or equal to sign is there for. So that's the tricky part of this question. You have to essentially calculate these two forces and figure out which one is bigger. If the static frictional force is bigger, your net force is going to be 0. And I just cancel it out. If this one is bigger, then you have to take the difference, and this thing is going to start sliding. It's going to start sliding across the table, and this one's going to start going downward. If the net force is 0, what will the acceleration be? Newton's second law. Excuse me. Newton's second law tells us net force equals mass times acceleration. If the left side of that equation is 0, the right side of the equation equals 0. Is the mass 0? No. So the acceleration has to be 0, right? If the net force is not 0, if you have some number here, then that equals the mass times the acceleration, but you have to include both masses. It has to be mass 1 plus mass 2 times the acceleration of the system. And then you can solve for the acceleration and calculate the acceleration. So you have two situations that can occur there. Does that make sense now? All right. Who else has a question for chapters 1 through 5? $25 in chapter 5? Man, you give me all the hard ones. I have to read through this to make sure that I'm going the right direction because this is a long problem. Okay, so banked turns. Have any of you been on a highway where the highways are banked? No? They have these in California all over the place. They're kind of crazy. See if I can find you a really good one here. Like in Oakland, there's one that's so severely banked, it's like you're on a racetrack. Not giving us a good view of one. That's a racetrack though. There's a great one there's a great bank in the highway on 580 here. You can kind of see it. As it turns here, you can kind of see it banking. That's like right near my house where I grew up. But there's these great highways that go through the hills, and they're like eight lanes across, you know, and they just bank through the hills like some kind of racetrack, and you know the traffic going through there is cranking along at high speed. It's pretty fun to drive on. But anyway, excuse me. Racetrack definitely are banked. In this particular case, we have a car that's coming straight at us. And we know it's a race car because it has no headlights, right? 24.2 degree banked turn. It's a pretty steep banked turn. And we want to know if the mass of the car is 600 kilograms, what's the weight of the car? Well, that's easy, right? What do you do to calculate the weight? It's just mass times gravity, right? Doesn't matter if it's banked or not. And of course, the gravity pulls straight down towards the ground. So if this is our banked turn, and then this is the ground, and then we'd go straight down, so that would be that one right there, right? It turns out if the car wasn't moving, the normal force on the car would be equal to a component of the force of gravity, and there would be some necessary friction between the tires and track to keep it sliding down the embankment. Okay? So what they're talking about here is this idea. Let's actually stay here. Let's go. Where's my drawing board? Here it is. Okay, so So here's our car. Here's our banked curve. Excuse me. I'm going to draw that a little more extreme. Here's our angle, whatever it is. And here's our car. And what they're talking about here is that the gravitational pull on this car is pulling the car down towards the center of the earth like this. That's the weight. And we're going to rotate our axes so that we have a perpendicular and a parallel axis, right? So this is our perpendicular axis. This is our parallel axis. And so we need a perpendicular component for our weight, which is going to come down like this, and a parallel component, a component that's parallel to the surface there. And this is going to be our weight perpendicular, and this is going to be our weight parallel. And what they're saying is that one of these components is trying to cause this car, so this is a force, right? The force is pulling the car down this way. But one of these forces is trying to make the car slide down towards the center of the track, the bottom of the track. Which one of these components is doing that? W perpendicular or W parallel? Which one of these is pulling the car down towards the center of the track? Or pushing it? The parallel one, because that's the one pointing that way, right? So the weight of the car, if you put a car like this on the track, and the track was covered in like oil, like just slopped with oil and grease, and you put a car on the track like this, it would just slide down to the bottom. And the reason is because the weight has a component that's partially pulling it that way, right? It's not all of the weight of the car. If it was all of the weight of the car, it would fall down like the car would just fall through the air. It doesn't go that fast. It just kind of slides down kind of slowly, right? So this weight component that's pointing in this direction will cause this car to accelerate down this way. But if there's no oil on the track and you put the car there, it doesn't do that. Why not? If there's no oil on the track, you sit the car on the pavement, what's preventing this car from sliding down the track? The tires have some friction with the road, right? And so there's this little friction force that points up this direction and counteracts this one. And all the friction on the wheels has to be equal to this right here in order for it to not slide, right? This force and this force have to be equal in order for it to not accelerate at all. Because forces have to cancel out so that they're all equal to zero so that the acceleration is zero. So we have two forces in this parallel direction. We have the weight force trying to pull the car down. We have the friction force holding it up. They add to each other and cancel out. And that is the idea there with that. So we do this problem using the equations that we have so far, or the Newton's equation. So Newton's equations say that the net force in either direction, right? Doesn't matter what direction. So let's say the net force in the parallel direction has to equal mass times acceleration. So right now we're dealing with the parallel direction. And guess what? The acceleration in the parallel direction is zero, right? And so that means the net force has to equal zero. But the net force, there's two forces. There's friction, which is going to be in the negative direction. Negative the friction plus the weight parallel has to equal mass times zero, which is zero. So this tells us that the friction equals the weight parallel. That's important, that's helpful. In the perpendicular direction, what do we have going on? We're also going to have the net force has to equal zero. Sorry, not necessarily zero, but the net force has to equal mass times acceleration in the perpendicular direction. But in the perpendicular direction, does the car move? Does the car ever jump off the road or fall into the road, in other words? No. In the perpendicular direction, this doesn't have any acceleration, doesn't have any movement, right? So that's also 0. And what are the forces in this direction? Well, we have the weight perpendicular, the perpendicular weight component pulling it down into the track. And we also have the track pushing on the car. And what do we call that force? Normal force, right? So the normal force is pushing upward in the perpendicular direction. So we'll call that the positive one. And then we have minus the weight perpendicular force pulling it down. And that has to equal 0 because it's not accelerating in that direction. So this tells us that the normal force equals the weight perpendicular force. Now both of these equations we're going to need to do this problem. Why? Well, because on this side we have the friction force, and the friction force is equal to what? What is friction equal to? Well, it's equal to mu static times the normal force. And what is the weight parallel equal to? Well, the weight parallel down here, we have this angle theta. The weight parallel is opposite that angle theta, so it's going to equal the weight times the sine of theta. Right? It's equal to the weight because the weight part of this triangle is the hypotenuse of this triangle, the longest side. And this is the side, this side here is the side opposite the angle, so that's sine theta times the weight. So this side of this equation equals weight times sine theta. Well, we know everything in this equation except the normal force. And let's see, we don't know the static coefficient. I don't know what we know, but there's something in here we don't know. And something we do know, and then we can solve that. Over here on this side, we have the normal force equals the weight force, the perpendicular weight force. Well, the perpendicular weight force is equal to weight cosine theta, because that's the one next to the angle. So now we know what the normal force is equal to, as long as we know the weight and the angle, right? So these two equations, with these two equations, we can solve for just about anything we need to solve for. Now let's go back to our problem and see what it is we need to solve for. Okay, so the car wasn't if the car wasn't moving, the normal force of the car would be equal to so that's what we just actually figured out. In our problem, the car is currently moving around the turn. Makes the normal force larger than the weight of the car. Say the driver wanted to go around the turn at the perfect speed where the car wouldn't want to slide up or down the track, go around a perfect circle. So we're actually going one beyond this. Hold on a second. Let me just check and make sure. Okay, so now we're going to add one more thing to this, apparently. So we're adding one more thing to this problem, and that is the fact that the car is now moving around the track. So moving around the track adds something. Wait a second. I think that this problem is actually in the wrong chapter. So this one, actually, we're going to have to use something from chapter 6 to solve. And I don't think that I realized that when I put it in the problem. When I put it in the problem set. Because to solve this one, we're actually going to have to use the centripetal force. Because the centripetal force is a force that holds the car in like this and has a component that's parallel and a component that's perpendicular as well. Like that. And I didn't take that into account when I was looking at this problem. What that means is you don't have to do the problem. So, yeah. Well, that's nice. I hope you didn't spend too much time on it, because you don't have to do it. Let's fix that really quick. Chapter 5. Which number was that again? 25? No. 25. So that one needs to go into the next chapter. Let's see, withdraw. So you get a free question. Way to go. So that one actually, that should give you just the full points on that question now. But that one needs to be removed. Sorry about that. That happens probably about once every 3 or 4 assignments as I'm going through these, because sometimes I write the question, sometimes I'm using a question written by somebody else, so it's not always immediately apparent which chapters it uses. And that one apparently does not match up with chapter 5 very well. It matches up with chapter 6 better, so I gotta make a note of that. So check to make sure that I gave you the points. If it didn't, send me a note, and I'll fix it. I'll try to fix it again. Well, that was a whole lot of talking for something we would do in the next chapter. Let's actually go ahead and finish it up, actually, since we are doing stuff for the next chapter right now. This will be useful still. Might as well make use of the time. So in this problem, you are going to have now this centripetal force that holds the car in. And what it does is the centripetal force points towards the center here of the track, towards the center of the turn. And that means that it has two components. It has a, oops, I drew that wrong. Let's see. That means it has a parallel component and a perpendicular component like this. This perpendicular component it's like extra normal force almost. And this is that feeling that you get when you're on a roller coaster or turning in a car or going up a hill or down a hill or up in an elevator or down an elevator where your feet feel like they're getting pressed into something or like you're like rising out of it, right? In this, the race car driver will feel like they're getting pressed into their seat by this force, because essentially what it is the ground is pushing on the car more as they turn around the corner, because the ground has to push on the car to turn it around the corner. And there's also this extra force here that has to be accounted for. Now, how do we counteract that force? Because what this force here is doing, is it's going to try to, a better way to say that is it needs to be here to keep the car turning around the corner, which means that we need more friction here to keep the car turning around the corner, right? And so if we have this friction, the static coefficient of friction equal to this friction, then they cancel out and there's no problem here, right? But if the static coefficient of friction is not enough to hold this here, these wheels are going to slide. And then the friction is going to decrease because the kinetic coefficient of friction is less than static coefficient of friction usually. And it's going to slide, so that'll be a problem. So the idea here is to make the turn the right angle so that this force here is equal and opposite to the static coefficient of friction for the tires, so that it balances out to be equal to 0. And then this force here is going to add on to our normal force. So we have our normal force that was here already. Where did I label the normal force? I didn't really label it. Oh yeah, I did. I kind of labeled it here. It's a lame arrow. It's a lame duck force. So here's the normal force, but then we have this added in extra force from the centripetal force, because this centripetal force is here. So this triangle here is going to have the same angle as this triangle here and this triangle here. Right here, it'll be right there instead. And then this one here, which is the parallel one, the force parallel, has to be equal to this. So then that gives us, before we had the frictional force and the weight parallel, but now we're going to add in another centripetal force parallel into this equation. So we'll have force centripetal parallel in this equation. And force centripetal parallel is going to be similar to this one, the weight parallel, in that it's going to have a theta in there and some kind of angle. But in this case, this one is next to the angle, so it's going to be the adjacent side. So instead of a sine theta, it's going to be a cosine theta. So over here we would add the force centripetal parallel to this one, and that force centripetal parallel is going to look like this. It's going to look like force centripetal times the cosine of the angle theta. So we have a new equation here. We've added on a new thing. And then also we also have to consider, what is the centripetal force? Well, centripetal force is equal to mass times centripetal acceleration. And centripetal acceleration is equal to the speed of the car around the track squared over r. So this is going to go in for this force centripetal in front of the cosine theta. And then that tells you everything you need to know to do that part of that half of the problem. But over here, we're going to have an extra normal force, right? We have the normal force equals the weight perpendicular force, and this weight perpendicular force is pointing down, but this centripetal force perpendicular is pointing up, so it's going to be on the side of the normal force. So it like increases the normal force. So we'll have the regular normal force which comes from the weight normally, right? Normally our normal force is just due to the weight, but this extra push upward here is going to add on to that normal force. So you can do this a couple of different ways. You can actually, let's see, you can actually, I would actually go back to the very beginning here and say that the normal force is going to, you're going to take the end of the normal force minus the weight, and then you're going to add on, so you're going to add on to it the force centripetal parallel here. Add on to it force centripetal parallel. In the end, what happens is that the normal force that they're talking about in this problem, they're saying that the normal force is increased by a force. That's the increase right there. So if you want to know what the increase is, you need to solve for F centripetal force parallel in this equation or in this equation or wherever else. But either way, that's how it comes into this equation. So, yeah. So that one's tricky for sure. Ooh, excuse me. Back in the problem. What is the net force on the car? So this car, if it's going at a constant speed around the track, which it is, actually only has one acceleration on it, and that's the centripetal acceleration. So that's the force. If you can calculate that centripetal force, then you can calculate the centripetal acceleration, or vice versa. Either way, the net force is the centripetal force, so it's going to be a force that is pointing inwards towards the center of the turn, and it's going to be equal to the centripetal force, or mass times velocity squared over r, or mass times centripetal acceleration. And then, of course, you can calculate the centripetal acceleration from that easily. Then they changed the rate. Then they Oh, and then they tell you the radius of the turn, and you can use that one actually in this equation here with the radius to calculate the perfect. So in that one, you actually solve for the radius instead of using the centrifugal acceleration. You plug this in and solve for the radius in this equation. So, but like I said, you don't have to do it for chapter 5. I don't know if it's in chapter 6 or not. Can't remember if I put it there or not. Let's go see. Looks like I did put it in there. So good thing we talked about it, huh? All right. Anybody have any other specific questions about that? From the equations that we worked through there, you can pretty much get every answer to that problem without any new equations. But you do have to kind of manipulate them properly and understand which one you need to solve for which part. I'll leave that to the student to figure out, but all of the information is there in that solution. Anybody else want to do another problem from chapter 5 or another chapter before chapter 5?
Could we do 28?
28 from chapter 5? Apparently I can't. I've already done this problem. The attempt. What is 28? No, this is not. That's not 28. What is this? I'm in the wrong chapter. Let's try this again. Chapter 5. That was kind of weird. There we go. Ah, yes. Another classic problem. So this one is very similar to the one on the table, except instead of the table being flat, it's at this angle, so you have to deal with it a little bit differently. It is definitely more challenging than the one on the table. Okay, so we have this mass 1 mass 2, right? Like this. Okay, so let's take a look. Question. Mass 2 has an initial velocity down the incline. And the kinetic friction coefficient they tell us. And they want to know the force of friction M2. Okay. Oops. So they're telling us originally that this thing has some velocity like this, down this way, right? Which means this one also has a velocity up this way of the same velocity, right? Because they're connected by rope. That's fine. So they want to know what is the force of friction here. So if this is moving this way, the force of friction will be this way, right? Because it always goes against the movement. And there's also a force, there's also some other forces involved here. There's the force of gravity acting down on mass 1. So that's the weight of mass 1. And then there's the weight of mass 2, which is acting down this way. It's weight 2. And we can break that into components since we have this incline here, we can pretty much guess that we're going to be doing a parallel perpendicular coordinate system thing here. So weight 2 is going to have two components. It's going to have the perpendicular component, weight 2 perpendicular, and then it's going to have this parallel component, which is weight 2 parallel, weight 2 perpendicular, weight 2 parallel. Okay. And those are all the forces that are involved here. That's it. So we do this in, let's look at, and also let's also remember here that we have the tension in the rope here that's pull this, so the tension, the rope is pulling the block this way on mass 2, and the tension is pulling the block upward on mass 1. We call this tension. And this tension, these two tensions are the same tension because they're the same rope. Tension transmits itself through the rope. So, and remember that we can add forces that are up and down into the parallel direction because they are transmitted to that direction through the rope, or essentially through this tension force here. Okay, so if that is the case, then we're going to do a parallel and a perpendicular part of this problem. Remember that we split this into two parts for the two dimensions. And excuse me. In this direction, in the parallel direction, we have the tension which is connected to this tension, which is connected to the weight, which is related to the weight of block 1. So that would be weight block 1. And it's pulling the block this way, which is in the negative direction. So we'll take negative weight block 1. We also have the friction that is pushing in that direction there. So that's also going to be a negative, we'll call it negative friction. It's the only friction in the problem. And then we have this force that is pulling this way. What force is pulling this way? Well, it's this one right here. And that's positive plus weight 2 parallel. And that has to equal, now what it says is that it has an initial velocity down the incline. So this essentially has to equal the mass 1 plus mass 2 times the acceleration in the parallel direction. Right? This equation is not going to give us very much just from looking at it. There's a lot of things we don't know in this equation. So we'll maybe come back to that. This one here is going to be the perpendicular direction. So what's going on up in this direction, this way? We have up this way, we're going to have the normal force, of course. And down this one, we're going to have the weight 2 perpendicular. And the weight 2 perpendicular is going to be the negative one again. Plus the normal force, that has to equal 0. That means the weight 2 perpendicular equals the normal force. Solving that equation. Well, this one might be a little more helpful. Let's see how it can be helpful. The weight 2 perpendicular is this side right here with this angle theta. This is the angle theta. And so that weight 2 perpendicular is next to the angle theta, so it's going to be equal to the weight times the cosine of theta. Yeah, cosine of theta. And that has to equal the normal force. Well, let's see. We do know the mass of block 2, and so we can calculate the weight. If we can calculate the weight and we know the angle, they did give us the angle, then we can calculate the normal force. So now we know the normal force acting on this block. We can calculate this. Well, that's nice because frictional force in this equation over here in the parallel region is equal to the mu kinetic friction, the mu of kinetic friction, times the normal force on the block. We know that. That can get plugged in right here, and we can calculate the friction. Once we've calculated the friction, we can plug in right here. Right? And then we're kind of off to the races a bit. Because once we plugged in the friction here, we know the weight of block 1. That's right there. We know the frictional force now here. We know the weight of block 2, the parallel weight of block 2 we can calculate. That's pretty easy to do. And what do they want to know? They want to know the acceleration maybe? They want to know the force. Well, the force of friction, we already calculated that. Magnitude of the net force, well the net force is equal to the mass times the net acceleration, or times mass times acceleration. So we can just do that. And then of course, if you know the net force on the system of masses, then you can calculate for the net acceleration. Either way, we're pretty much done at that point. We are done at that point. Because we've calculated where did my whiteboard go? I thought there we go. Okay. So because we've calculated these things here are all, if these things added together are all the net force. So we've calculated this, and we can calculate that. You can get the net force that way. And then if you want to know the acceleration, then you just set that force equal to m1 plus m2 times the acceleration on the whole system parallel, and you'll get that acceleration of the whole system. So this thing has everything we need. The great thing about teaching in the afternoons during the summer is when it's 100 degrees outside, we'll be comfortable. Terrible thing is that it's always drowsy in the afternoon. I don't know why I feel drowsy. I got a good night's sleep. Besides, I didn't eat. Yeah. Any questions about this? Does that kind of clear it up, clear as mud? Any more questions? Anybody has? Chapters 1 through 5. Any more chapter 1 through 5 questions, anybody?
26.
26 on chapter 5? Oh, yes. So this is, again, actually similar to those problems, but a little more straightforward because we don't have the angles to deal with. But this one is tricky because it's tricky in its own right because of the connecting rope, which makes this all one system again, right? And so if you pull on this box here, which is exactly what they're doing, then this box is going to have essentially 3 forces acting on it. It's going to have a pulling force here, and it's going to have a tension force pulling backwards here, and it's also going to have a frictional force pushing back on the box here. So to find the net force on this box, you'd need to know those 3 forces. However, the whole system has a pulling force on this box, a frictional force pulling backwards here, a frictional force pulling backwards here, and then the connecting rope forces in the middle just cancel each other out. The tension cancels itself out. So it's like a pull and 2 frictions. Right? So how do we write that down? Oh, dang it, I'm on my whiteboard still. I always do that, switch to my whiteboard without switching back to my book. So here's what it looks like. We draw it. Box 1, box 2, whatever they are. They're both on the same surface though, even though mine don't look like it. So you have this force pulling this way. Then you have friction 1. Friction 2. Goodness, I'm writing fast and it's terrible. Right? So here are all the forces. Friction 1, friction 2, forward pulling force. And that's pretty much it. So you have forward pull minus friction 1 minus friction 2. Those are all your forces. When they add together, they have to equal the mass times the acceleration of all the blocks. That means the mass is mass 1 plus mass 2. Goodness. Mass 2 plus mass 3. Right? Times acceleration. And what they want to know is what is the acceleration? So solve it. Make sense? Simpler, but a little tricky, especially because you have the two frictions involved. Anybody else have questions from chapters 1 through 4, 1 through 5?
Would you be able to go over number 18? The way it's worded confused me a lot.
Number 18 in chapter 5?
Yep.
Sure. What is the force of friction an object receives at the coefficient? Oh, I see. I see now what's going on. It's a typo. So this is supposed to say, what is the force of friction an object receives if the coefficient of friction between the object and the surface it is on is mu and the object experiences a normal force of F sub n. So there's supposed to be an and right here. So that would be confusing. But what they're saying here is that they want you to write a formula for this now. So the force of friction is always mu times the normal force. So we would put in mu and then we would multiply times capital F into a sub n, and then we would submit that. Just like that. So, sorry for the typo. I can fix that one too. To fix it, I have to go into the problem a different way. I can't fix it from here, so I'll have to fix it later. Any other questions? In fact, I just had a brilliant idea. I have a student working for me this semester fixing problems, and I'm going to have him fix that problem in the next semester's homework problems. Is that number 18?
Mm-hmm.
And which is the one we needed to remove? We'll just send that to him and he can fix them. He's supposed to be learning how to do that stuff. And I hate coding. I hate writing computer code. He's still young, or he's younger. He can sit at a computer longer than I can. I get up from this class and I like have to limp out to my car. My legs get all stiff and sore from sitting so long. I suppose I could stand up. Not really comfortable to stand up on this floor. I need to get one of those thick, spongy, like Standing pads. That's what I need. I'm going to go buy one of those. All right. Anybody else have any questions? Chapter 5, 4, 3, 2, 1. Okay. If there are no more questions from chapters 1 through 5, then make sure that you contact me about any questions you might have before you take the test, so I can help you out with them. I will answer questions tomorrow and Friday as much as I can. So let's see. Let's move on to chapter 6 then. So in chapter 6 we covered the first two sections, which are rotational angle and angular velocity, where we learned about how to find things using a rotation and a distance kind of thing, and then we talked about how rotation can have a speed to it, so you can rotate at different rates. You can have a slow rotation or a faster rotation. Angular velocity. We learned about radians versus degrees, how to convert those things. And then we learned about centripetal acceleration and what it is that keeps something going in a circle, which is an acceleration that actually points towards the center of a circle, right? And centripetal acceleration came from this idea: is if you have a velocity along the edge of a circle this way, and then later on the edge of the circle your velocity is this way, and then you take the graphical difference between those two vectors, you do get a vector that points towards the center of the circle like that. And we had some things that we calculated. For example, we calculated that acceleration as the velocity squared over r, or the speed on the edge of the circle. So this works. We call this the tangential speed, or the linear speed on the circle. This works as long as you're going around the circle at a constant speed. So you can use this equation, very good equation. Also this equation using the angular velocity squared, r times angular velocity squared. Then we did some simple problems with that, not too big of a deal. The next part is now, the next thing for us to do is to talk about centripetal force. If you can have an acceleration that keeps you, if you have an acceleration that keeps you going in a circle, then there's of course a force associated with that acceleration. And the centripetal force is just going to equal the mass that is being accelerated times the centripetal acceleration. If you're on a circle going around and around at a constant speed, then you can use those same equations, v squared over r or r omega squared, to make these equations for the centripetal force. And you can also solve for the radius of the circle that you're going around. So if you know how much force something is receiving, you know how fast it's going, you know its mass, you can actually calculate the radius that it's at. And that's kind of useful. One of the things that this teaches us about this is that things that are going in a circular path, if they have the same mass and same speed, if they're going in a small circular path, they have a bigger force. Or if they have a bigger force, they're going to go in a smaller circular path. And the same thing if they are experiencing a smaller force, they're going to have a bigger circular path. So this is well known to people who drive cars. You know that if you take a really, really tight turn with your car at 25 miles an hour, your wheels are much more likely to skid. And that's because there's a lot more force involved to turn a car at a very, very small radius. So sometimes your tires can overcome that, sometimes they can't. But if you take a bigger turn at the same speed, 25 miles an hour, you're less likely to skid your tires, because the friction between the tires and the road is enough force to overcome that smaller turning force for the larger radius. And that's exactly what they do here, is we're going to calculate what coefficient of friction the car tires need on a flat curve of a particular radius with a particular mass of the car. So they just plug in the mass of the car, which is the 900 kilograms. The speed of the car, they're going to do 25 meters per second, like 50 miles an hour. And then the radius of the turn is like 500 meters, right? So they plug all those in there, and it turns out you need 1,125 newtons of force to turn that corner. And that force has to come from friction, right? So then if you use that value for your force and plug it into a friction equation, mu times n, the normal force on a flat turn, then you can use the weight for the normal force because it's on a flat turn, just m times g, and calculate what coefficient of friction you're going to need. And this is the kind of thing that road engineers do, and also highway patrol officers who are investigating crashes, and also highway patrol. The people that work for the highway patrol to determine the speed limits that should be on certain turns on roads and highways and things like that. They use this equation. It turns out that the mass of the car doesn't even matter for the turn, which is great because different size cars, masses of cars go around turns all the time. You wouldn't like to have a different speed limit for every kind of car. So it turns out that the mass cancels out on each side, and the coefficient of friction between wheels and tires going around a turn is dependent on the speed of the car, the radius of the turn, and then gravity, which is constant anyway. So speed of the car squared times the radius of the turn, or divided by the radius of the turn times gravity. So they do that here, and they solve it and find out it needs to be 0.13, which is about the coefficient of friction between rubber and concrete. Well, we hope it'd be a little bit greater than that. So this is what the free body diagram looks like on a car turning on a flat turn. But if you're on an incline turn, which is the problem that we've got in the homework, this is what it's going to look like. You're going to have this normal force that is up at an angle. You're going to have the weight force that's here. You're going to have this. You're going to have the normal force providing some of the centripetal, providing that centripetal force inward. Right? So this one is actually a better, if you're going to do that problem in the homework, I would actually use this one. This drawing does a better job of depicting what's going on there. Because I followed what they were doing in the book, which kind of does this backwards. But the normal force pointing upward is what's pushing the car towards the center of the curve. So this little piece right here is your centripetal force. That right there is the centripetal force on the car. Okay. Can't remember what I drew. Let's see what I drew and see how it's different. Oh, it's not there anymore. Anyway. So, for the car on the turn, the ideal way to think about this is actually from the example in the book, where you have a car on the turn. I'm just going to show it as a block. And there's a normal force upward. There's the weight force downward. Right? And the normal force, well, the weight force is going to have this component. You could think of it as kind of components this way and this way that are parallel. But the normal force is going to have this component in the xy domain. If we use our units, use our dimensions x and y like this. This one has this component that points straight this way, which can be very useful in a turn, because that is going to be the centripetal force component. Right there. Which happens to be, this is theta here, that ends up happening to be the normal force times the cosine of theta. Is your centripetal force in that problem. Oops, I said that wrong. Nobody caught my mistake. This is opposite that angle, so this is normal times the sine of theta. Sine of theta. This angle is opposite this side right here. Normal times sine of theta equals centripetal force. Sound good? All right. So let's go back to here, not here, here. Okay. So in this example, they do exactly this. They do calculate this this force down here. So normal times sine of theta is the centripetal force. Normal times cosine of theta is equal to the weight, so they do calculate that one as well. And that one gets calculated by rotating the axes. But in the end, you got these two things here, weight over centripetal force, normal cosine theta, normal sine of theta, and they end up equaling, that's what they end up doing up here, actually. So you have, on one side, you have the normal cosine of theta, and on the other side, you have the normal sine of theta, and you end up getting the tangent of theta equaling v squared over rg. Just like that. So you can either do it all over again, or you can just write it down. So this equation essentially is telling us what angle, so if you solve this equation for theta rather, it'll tell you what angle the bank of a curve has to be so that you can turn around it without sliding. So that just going around it, you'll go around it without having to use the friction in your tires to go around it at a particular velocity and a particular radius. If you solve it for v, it tells you how fast you can go around a turn with a particular radius and a particular angle. But you can also solve it for r, and it will tell you what the radius needs to be for a particular angle of slope and a particular speed. You can solve it for anything you want. In this case, they do solve it for v, and they get this equation, 45.8 meters per second of speed to go around this particular turn. Now we're going to learn about a couple of other forces that are not things that we can calculate much with in this class. Requires a much higher level of mathematics, but they're interesting just the same. The first one, and all of these forces are considered by physicists fictitious forces. They're forces that don't really exist, but they seem like they exist when you're in this situation. And the first one is the one that we're all familiar with, which is the centrifugal force. This is that force that you feel when you turn a corner, and you feel like when you're turning a corner right, you feel like you're being pushed left into the door. That's the centrifugal force, which is, of course, not really a force that is making you go that way. What's happening is you're trying to go straight, and the car turns in front of you, and you run into that car, right? You run into the door. And then the door pushes you back into the circle, and that's the centripetal force that actually turns you with the car. So that is not a real force. It's the centrifugal force is not a real force. It's the centripetal force that is. I know it's confusing, but anyway. There are other forces that are like this as well, though. One of them is called the Coriolis force. So the Coriolis force is a force that that causes things to rotate instead of just causing some like this linear motion towards the outside of the car or whatever. This is a rotational force that is that actually does seem like it's real because it's quote unquote responsible for things like hurricanes. But hurricanes are not really caused it's not this Coriolis force that's causing them. Actually, they're caused because there are winds that are moving and clouds that are moving within those winds that are moving in straight lines on the Earth, but the Earth is rotating underneath them, right? And so relative to the Earth, they're actually spinning, right? But relative to the rotation of the Earth, they're actually going in straight lines, if that makes any sense. But because the Earth is rotating, they certainly are, as we look up into the sky, it seems like the sky is rotating in the middle of a big hurricane or whatever. It's not actually true. If you looked at the storm as it rotates, as if the Earth wasn't there, and you were just looking at the clouds moving through space, they would be moving in a straight line. But whatever, right? So the point is that relativity really plays tricks on people who are in reference frames, different reference frames. But we don't really care because the storm still causes us trouble. But the really interesting thing about it is that in the northern hemisphere, you will get a counterclockwise rotation of these storms. But in the southern hemisphere, you get a clockwise rotation of these storms. Because they're on different sides of the equator, they behave differently. It causes a different relative effect on the storm. So it looks like they're rotating in opposite directions. So it's kind of interesting. And they call them different things too in different places. So not called hurricanes everywhere. In Australia, they call them Willy Willies, which I think is hilarious. So anyway. So let's talk about Newton and the falling apple. This is a great watercolor painting in the Japanese style of Newton's experience with the falling apple, right? Well, one of the things that's grossly misunderstood about Newton, especially when students take physics, is they think that the thing that Newton discovered about force was just force equals mass times acceleration, which isn't exactly true. What he really discovered, one of the greatest things that he discovered, and was that forces between all objects of mass have this relationship that is very specific and particular. And it's called Newton's universal law of gravitation. It's totally true that Newton did, come up with the Newton's second law, the force equals mass times acceleration. But it's a little bit understood when it comes to gravity. What he discovered when it comes to gravity. A lot of times people think that Newton discovered that the gravity on the Earth is 9.8 meters per second squared acceleration. That's not Newton. That wasn't Newton. That was actually Galileo. Galileo discovered that. What Newton discovered is that all mass attracts all other mass. So even you and I in this room, we have this attraction between us that is completely due to our mass. But it's really tiny because our masses are really tiny, right? The Earth, on the other hand, has a humongous mass. And so it attracts all of us much more than we attract other objects. Humans will never really attract other objects enough for the other objects to notice it, right? But the Earth is so huge that we really notice that attractive force, right? The Earth doesn't notice our attractive force at all, but we do attract the Earth towards us. We're pulling the Earth towards us, in fact, with the same amount of force as it's pulling us towards it. But it's so massive that that amount of force is just not very, it doesn't do anything to the Earth, So 200 pounds of force doesn't move the Earth at all. Another thing that Newton was able to determine was that the forces acting on two massive objects always act on a line that connects their center of masses. So if you draw a direct line between the center of mass of two objects, that is where those forces are going to act. That's the direction they're going to act, towards the center, towards each other along that line. and also that the distance between them is important, and that that distance has to be measured from the center of mass of the object. So this is actually why the force between us and the Earth is the same for everybody on Earth. Because everybody on Earth is an equal distance from the center of the Earth, pretty much. And so that's why gravity acts the same everywhere on Earth. It doesn't really act the same everywhere on Earth. If you go to the top of Mount Everest, gravity is actually weaker on the top of Mount Everest than it is at the bottom of Death Valley. Because there's 30,000 feet difference between those 2 points, the highest point on Earth and the lowest point on Earth. I can't remember if Death Valley is the lowest point or if it's the one at the Dead Sea. Let's find out, just because I'm curious. Lowest point on Earth, not in the ocean. The Dead Sea. Yeah, it is the Dead Sea. Oh, that's the Mariana Trench. Yeah, the Dead Sea Depression. So that's the Dead Sea is east of Jerusalem in Israel. Not far from Jericho. But anyway, it's like 300 or 400 feet below sea level or something like that. Anyway, so that's where it is the strongest on Earth, at least on land on Earth. And then it's weakest at the top of Mount Everest. Anyway, so this whole law thing that he came up with boiled down to a few different things that he discovered. He discovered that mass matters. How much mass something has matters. So the 2 objects, if you multiply their masses together, that turns out to be an important part of this law. Then if you divide by the distance squared between them, it has to be between their center of masses. So distance squared between them is the r squared, and then you have to multiply by this constant every time. In order for the masses multiplied together divided by the distance squared to equal the force, otherwise it's just proportional, but in order for it to be equal to the force, you had to multiply it by this tiny, tiny number, 6.67 times 10 to the minus 11. And then the units for this constant, this is what we call a universal constant. Whenever you build an equation that gives you a proportionality for problems, a proportionality. So in other words, the answer is proportional to the right answer, but it's not equal to the right answer. But if you find a number that when you multiply it by that or divide it by that or something like this, and it gives you the right answer every time with every situation, then we call that a universal constant. And physicists and scientists in general are always looking for these kinds of things because they're usually really important in nature. And this is one of them. The universal gravitational constant, G, is the thing that kind of makes this equation work. And so if you take the mass of the 2 objects, multiply them together, divide by their distance squared between them, and multiply by this, it will actually equal the force that is actually between them. The amount of force that you measure between them using some kind of device, like a scale or whatever. So this is a number you should remember, and this is an equation you should remember. It turns out that when you apply this equation to weight, so weight is equal to the mass of an object times little g, 9.8 times 10, or 9.8 meters per second squared, then, and you set them equal, which is what they're doing right here, and then you solve for little g. Little g is equal to big G times the mass of the Earth divided by the radius of the Earth squared, which makes perfect sense. This would be the acceleration that anything feels, any mass feels on the surface of the Earth. If you want to know what acceleration any mass feels on the surface of the moon, you just replace this m here with the mass of the moon, and this radius here with the radius of the moon, and you're good. If you want to know the acceleration that the moon feels relative to the Earth, that the moon feels from the Earth, Then you plug in the mass of the Earth, and you plug in here the distance between the moon and the Earth squared. And those are the kinds of problems they'll have to do. Here, they're going to find the acceleration due to Earth's gravity at the distance of the moon. So they calculate that right here, using the mass of the Earth for m, but they do the distance to the moon, r squared. So the distance to the moon is 3.8 times 10 to the 8 meters, which is 384 million meters. Then they square that, and this is what you feel. This is the amount of acceleration you feel when you're at the moon due to the Earth's gravity. It's hardly anything at all. It's 2 millimeters per second squared. That's how much the Earth pulls on you from the moon when you're on the moon. Not much. You can also do this calculating this from the speed of the Earth, or speed of the moon around the Earth, which is what they're doing this way, the angular speed or the linear speed either way. And we kind of talked about this before, I think, where the did we talk about the orbit of the Earth being affected by the moon? Or was that in the previous class? I don't remember. But anyway, because the Earth pulls on the moon, but the moon also pulls on the Earth, right? I think we talked about it. But anyway, the Earth actually gets pulled back and forth in its orbit and has this funky shape to its orbit, this green path. Also, the tides are affected by the moon and the Earth. So the Earth pulls on the water and keeps the water on the Earth. But when the moon is on one side of the Earth or the other, this water on this side gets pulled a lot towards the moon. And this water over here doesn't get pulled so much towards the moon. And this water on the side kind of gets shifted and fills in the space. So water gets pulled from the sides to go over here, and it kind of gets left on this side a little bit. So you get high tide and a really high tide over here. And there's actually different versions of this. When the sun and the moon are both on the same side of the Earth, you get a bigger tide. When the sun and the moon are on opposite sides of the Earth, you get a bigger tide. But when you have the moon on one side and the sun on the other at a 90-degree angle like this, you get this kind of weird tide called a neap tide, where you do get a stronger tide this way, but it's not as strong as this one or as strong as this one. And of course, this happens at different times of the month because the moon travels around the Earth on a monthly cycle, right? And then you have the crazy things like black holes. So a black hole is an object that has become so massive and has so much mass. It's usually a star that has so much mass, and it's grown and grown and grown, and then it collapses because its own gravity is too much for it to stay apart. So its own gravity actually pulls it together and collapses it. And when it does that, it goes through a process where everything in the star is turned into a neutron. Sometimes. It doesn't always do this, but sometimes it does that. Where everything is turned into a neutron, so it collapses even further, and it gets as small as an object can possibly get. But it still has all of its mass. So imagine you take the Earth and squish down all of the mass of the Earth down to the size of a marble. That's going to be one massive marble. And that's what a black hole does. And it can be the size of a marble. It can be very, very small. When a star becomes that dense, when the mass is packed into such a small place, the gravity that you experience when you get close to it is extremely, extremely high. Because the r at the bottom of the equation is extremely small. That r squared becomes very, very small. And so if you have a very, very small number squared, it becomes even smaller. And 1 over a very, 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 very small number is a very, 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 very big number. So the gravity becomes huge. And at that point, everything gets sucked into the black hole if it comes close enough. There's like this point of no return where an object gets so close that it can never get away from it. And it just gets sucked in and becomes part of the black hole. And it can be so massive and so strong that light sometimes can't even escape it. Now that makes a little sense to people since light has no mass. But it turns out that light is affected by mass. And that's due to our friend Uncle Albert up here, Albert Einstein. In 1905, Albert Einstein wrote 5 papers that changed all of science. Not just physics, but all of science, and even changed mathematics forever. And that's why he's widely considered to be not only the greatest physicist of all time, but maybe the greatest scientist of all time as well. Just in one single year, cranked those out. And the black hole is one of the things that that was a result of that science. Very interesting stuff. And then you have weightlessness, where you don't feel gravity because there's nothing pushing against you. For example, in the space station is accelerating towards the Earth at the same rate that the space people in it, the astronauts in it are. So they're both moving towards Earth at the same speed, right? Or they're being accelerated in the same way. So it's like being in an elevator that's falling, where you cut the cord of an elevator and it just falls. Well, the elevator falls and you fall with it, so you're not pushing against the elevator. It's not pushing against you. You feel weightless until you hit the bottom. Then you feel a lot of weight in a very short time, right? And that usually ends up badly. But weightlessness on an International Space Station isn't the lack of gravity. It's not because gravity isn't present. It's because gravity is acting on the space station in the same way that's acting on you. Now, pilots feel this all the time. Have any of you been in a small plane before? Or a big plane that's had a lot of turbulence? You've been in a small plane before? Has the pilot ever done anything to you, like cut the throttle or anything like that, and made the plane drop? No? What a terrible pilot. They should have done that. It's really fun. Have you ever been on a roller coaster where the roller coaster drops suddenly and you feel your stomach go, right? That is literally your stomach losing its gravity. So it's not pressing on the bottom of your abdomen anymore. It's actually pressing on your lungs. And that creates, and the stuff in your stomach actually moves. Like the liquid in your stomach will actually lift up and kind of be suspended in air. And that makes you nauseous. That is the feeling that makes you nauseous when you're weightless. Pilots get used to this all the time. Astronauts, of course, have to be used to this because they're in that situation constantly. They're constantly feeling that experience. So, let's see. So there was an experiment done after Newton figured this all out to prove this was true. Newton used the movement of the planets to figure it out. But this experiment was done on Earth with this guy named Cavendish. And they actually have his actual laboratory, I believe, preserved, or a recreation of it. So the building is still there because the building was at I think Cambridge. It's at Cambridge. It's at Cambridge in England. So it's not a building they get rid of anytime soon. But the actual apparatus used, I believe they've also. So here they've actually either, I can't remember if this is an actual preservation or if it's just a recreation. But what you're looking at here is a room that's completely sealed up so that there's no air currents inside, because air currents really mess up this experiment. And then you have these massive hanging balls in here, and there's some smaller ones that you can't really see right here and here. And the idea is that you let this all just kind of sit in here, and you rotate these things so that they're not near each other. So in here you can see it a little bit better in this one. So you have this, these two stationary ones, and this one that can rotate on a string or whatever. And as it rotates on a string, there's a little mirror you look at, and you can measure how fast it's moving, and how that would measure that, and from that you can measure how fast they're accelerating towards each other. But they're not going to accelerate very quickly, and if there's air currents in there, they won't accelerate at all. But as they do accelerate, if you look into this chamber, and that's why they have these little, there are these little telescopes you can look inside the chamber and look at this rotation. As they did rotate, he was able to measure how fast they were rotating and calculate the acceleration from that. And it turns out that Newton's calculations were correct. That they did depend on the radius of the distance squared between them. It was inversely dependent on the inverse squared between them, and it was directly related to the product of the masses. And then he was able to calculate g to a very high precision using that. So cool stuff. So that's Newton's law of universal gravitation. And then the last section is about Kepler. Now this is not necessarily in chronological order. I think Kepler came before Newton. But Kepler actually came into, he was able to figure out some interesting things about planetary motion. So again, this is motion around things around each other. But what Kepler discovered is that, first of all, even though the planets' orbits look circular in many cases, they're not. None of them are. Planets have elliptical orbits. Now, an ellipse is a particular shape that can be made in this fashion, where you put like two pins on a board, and then you put a piece of string that's tied to each of these pins, and it's a certain length. In fact, you can just make a loop of string. So this might be a loop of string, and then you put the loop around these two pins so to keep it tight. So this is tight here, and this is tight here, it's tight here. And then you put a pencil in this edge, and you keep it tight, and you draw around these pins, and it will create this oval-y shape. Now the shape of the oval will depend on a few things. If you move these pins further apart, the shape will get longer and skinnier. It'll be a longer and skinnier oval. If you move them closer together, it'll be kind of more circular. It'll be closer and closer to a circle. In fact, if you put the 10 pins right on top of each other, it will be a circle. So a circle is just a type of an ellipse, and this shape is called an ellipse. These 2 points where you would put these pins are called each of them are called a focus, and together they're called a foci. They're called foci. That's the plural for focus, F-O-C-I. And if you put the sun at one of the focus, at one focus, then all of the planets follow a pretty elliptical curve around the sun. So the Earth has an elliptical curve where both of the foci are actually in the sun. They're both close to the center of the sun, but not exactly there. So, but place like Uranus has an orbit where one focus is in the sun and one focus is outside the sun. It has a much more elliptical orbit, as does Pluto. Has a much more elliptical orbit than Earth, where Earth is closer to a circle, but still elliptical. So that's the first law of Kepler, is that all of the planets move in elliptical orbits. The second law of Kepler actually led to Newton's law of universal gravitation, and that is that as planets go around this circle, they sweep out equal amounts of area. So if this planet moves from point A to point B, it would sweep out this pie-shaped area as it did it. And if it went from C to D, it would sweep out this different pie-shaped area. But if A to B and C to D are both 5 days or 5 weeks or something like this, then these areas would be the same area. They'd be the same amount of area. even though they look very different, like this is long and skinny and this is kind of short and squat, they would be equal areas if they were equal number of days between the points that they sort them out. That is a direct result of gravity having a 1 over r squared kind of relationship, which of course is what Newton discovered. And you can see the r squared in this equation. In this equation it says that the time squared, sorry, you can see it in, you can't see it in this one actually because this is r cubed. That's okay. It does come from the same equation, but the area part gives us this r cubed factor. But anyway, the times you have this in this thing here, the time squared is the amount of days that has passed, and the r squared is the radius or the distance between the sun and, let's see, I think they want to know the major radius. No, the average radius. It's right here. R is the average radius. So the average radius of this planet's orbit. Now, the real value of this equation is that, that one was the equal times and equal areas is second law. Kepler's third law is actually related to it. It's actually related to it, but not the same. But the value that this equation in Kepler's third law has is really important. Essentially, it helps us to calculate different times that a planet is going to take to go all the way around the sun, or around the sun, or around another thing, like the moon around the Earth, or whatever else. So this equation, this second law was very important for figuring out Newton's equation of general gravitation. But it also leads to this law, Kepler's third law, and it gives us an equation for calculating how long it takes a planet to go around something, if you already know how long something else takes to go around. So how would you do this? And this is really the only law that we can use to do any math with. We can do any kind of example with. So they do it here. They say the moon is going around the Earth in 27.3 days. And its distance, average distance, is 3.84 times 10 to the 8. So this right here is the big T for the moon. And this right here is the radius for the moon in this equation. So if we say that T1 is the time for the moon and R1 is the radius for the moon, we put those two things in for that. We square the time and we cube the radius. And then here they say they want us to calculate the period, which is the time, of an artificial satellite orbiting at an average altitude of 1,500 kilometers above the Earth. So 1,500 kilometers is going to be 15 million meters, because kilometers is 1,000 meters, right? So 15 million meters is going to be our altitude, or our distance, or r. Actually, we have to add to that the radius of the Earth as well, because that's above the Earth's surface, right? Whereas we want from the center of the Earth. So we add the radius of the Earth to the 15 million meters above the Earth's surface, and that will be our r for the satellite, and then we plug that into the equation, and we get, we solve for the time for the satellite. So that's exactly what they do here. They're solving for the time of the satellite first, and then they get this equation, and then they plug in all those numbers. And they get 1.93 hours for the time for the satellite to go around. So 2 hours for a satellite to cruise around the Earth if it's 15 million meters above the Earth. Which incidentally is a little bit higher than the first person who ever orbited the Earth. I can't remember if he was the first person or just the first American. Let's find out. This is good stuff because John Glenn is an American icon. John Glenn. John Glenn, first American to orbit the Earth. So it was a Russian that orbited the Earth first, and he was the first American. He did it 3 times, and his flight lasted probably about 45 minutes, I want to say. So he was going even faster. I can't remember exactly how long this flight was, but actually it might have been an hour. Friendship 7 flight. It was where did it go? 4 hours 55 minutes. So it's a lot longer than I thought. He went 3 hours around in about 5 hours. So he was at 1.29 million. So he was almost as high as our satellite. Not quite. A little bit lower. A little bit shorter time. So those are Kepler's laws. Here they do the relationship between Kepler's and Newton's laws, like I was talking about. But here is a chart of all the different, let's see, we've got the different periods for things. So the Earth and the Moon, the period is this is in years, so 0.07 years for the Moon to go around the Earth. And it's a radius of 1 times 10 to the 19th. No, this is actually radius cubed. So they've actually cubed the radius. Here's the actual radius. 3.84 times 10 to the 5th kilometers. Mercury going around the sun goes around in 0.2 years. So a quarter of a year it goes around the sun. Venus, about a sixth of a year. Earth, of course, is 1 year. Mars is about almost 2 years. Jupiter goes around every 12 years. Saturn goes around every 29 years. So in most of your lifetimes, Saturn is only going around the sun once, or not even once, right? In my lifetime, it's gone around 1.5 times. Neptune, none of us are going to see Neptune go all the way around the sun. You know what the really amazing thing is? Is that this year, even though some of these planets go around the sun very, very rarely, you know, like Pluto, 248 years, it goes around the sun every 248 years, all the planets were on one side, on the same side of the sun for this last year or the year before. It's pretty amazing, actually. And then you have Jupiter, all of the moons of Jupiter here, Io, Europa, Ganymede. We actually made a model of the solar system 2 years ago for a summer camp here at the college. Some high school students and I made a model of the solar system. Here at the college, pretty much almost all of this was on the college campus. The sun was 2 meters in diameter, so about 6 feet, a little bit. And then about 50 yards away, maybe, you had Mercury, which was the size of a very small ball bearing. We actually made each one of these things. So we had Mercury, the size of a very small ball bearing. Then we had Venus, which was the size of a small marble, and it was about 50 yards away from Mercury. It's about 100 yards away from the sun. And then about 200 yards away from the sun was the Earth, which was about the size of a marble, small marble. Mars, also the size of a small marble, was another 100 yards away. So each one of those was about 50 more yards away. So all of those were on campus, from sun to Mars. The next thing, which is Jupiter, was all the way at the end of Willow, where Willow meets where the kind of where Taco John's is down there on the side of the freeway. So it was down by Taco John's. That was Jupiter. Then where the War Memorial Park is on the lawn near the freeway was Saturn. And then Uranus was, or which one's first? Uranus or Neptune? I think Uranus. So Uranus was at Nebraska Land Bank, Neptune was at the Children's Museum downtown, which is kind of near the jail there, next door to the jail, which is weird to me. And then Pluto was out at the river at Cody Park. And so Jupiter was the size of a basketball-ish, a little bit bigger, a little bit smaller than a basketball, a little bit bigger than a volleyball. Saturn was about the size of a volleyball. Uranus was the size. Uranus and Neptune were both the size of a pool ball. And then Pluto was a size of a very, very, very tiny ball bearing. It was super tiny. It was almost, it was the smallest piece of metal sphere I could buy. And we had all those planets set up with signs. And at that size of the solar system, the speed of light is kind of like a casual walk. It's like just kind of walking is how fast light speeds through. That's how fast light would be going through the solar system. So light takes like a couple of hours to get through the solar system at that speed, at that size. At any size, really. It was fun. It was a fun project. That finishes up chapter 6. So now we can answer any questions you might have from chapter 6. I know there were some questions. I don't know what they were, but who has a question from chapter 6 they'd like to ask? Anyone? No questions? Well, if there are no questions from chapter 6, we can be done. You guys can get ready for your chapter 5 exam or start your chapter 6 homework or just have a nice weekend. We will meet again on Monday and answer any other questions you have from chapter 6 and get started on chapter 7. So be ready for that on Monday. Did we get all your questions answered for chapter 5? You have a couple more? If you don't have any questions, you don't have to stay if you want to.
12. I think pretty much like 12 and 15 are the same thing. So I think once I figure out what I did wrong there, it's the next.
Yeah, okay, so these ones are a little bit tricky because they're already moving, right? So if it's traveling south and receives a push to the south on the surface, then you have so your object is already moving south, right? With some velocity initial. And then it receives a force to the south, right? A push to the south. Then that means it's going to accelerate, right? There's a P, 0.65. But what that really tells us is that what that's really going to do for us, because it's already moving when it receives this push, that means that the coefficient, that means that the friction is going to be a static friction. So it's going to receive a force this way, and it's going to feel a friction that is going to be a kinetic friction, right? Backwards. So the net force is going to equal the force to the south minus the friction kinetic. So the kinetic friction, of course, is going to be calculated using the kinetic coefficient of friction times the normal force. The normal force you're going to calculate from the mass because we're going to assume it's just on a flat surface, right? Or does it tell us the friction? No, it tells us the coefficient of friction, right? Oops. So this is going to be these are going to be the equations you're going to use where the normal force equals mass times gravity. Right?
So then with the, in order to do coefficient of friction problem, there were the units,
Yep. Is that what you were doing?
I don't remember that.
Okay. Yeah, so you're going to plug in that coefficient here along with mg. Mu times mg will be your force of friction. You'll subtract that from the pushing force to get your net force. And then you'll tell it the direction. It won't want positive or negative because it asks for direction later. Does that make sense? And the real key here is to just kind of keep track of directions and whether it's moving or not moving and that kind of stuff. Okay?
I have a question on 13. I was
Question?
doing it somewhere and I got messed up.
So this is the same one except going north. Yeah, so it's actually the same exact problem, just going north.
Okay.
Yeah. Just the other direction. All right, are we good? No more questions?
Yeah, I think the only other ones I have left were
Okay. All right, sounds good. Have a good one.